For the Synoptic QA/QC demo, I'm going to use standalone LP360 because LAS File Analyst is going to be a part of our QA/QC process. I am going to be using the, Viewer Integration Toolbar and the LP360 Point Cloud Tasks toolbar. I'm going to add all the Davidson County data. And in this case, I don't need all the actual data right away. I'm just going to be looking at the header, so I'm going to load footprints only. To have a backdrop, I'm going to add an image. I can't add the mosaic image that was provided with the dataset in LP360 because it's in a different projection, but I can use a WMS layer. And I'm going to use, let's say, Bing Aerial with labels. You can choose from a number of different web services for a base map. Before I get too far into this, I'm going to establish a project path so I don't continually have to specify the full path for the files that I'm going to create. So I'll go to File, Project Settings, and in the project path I'm going to go to a folder that I've made for this demo. And I'm going to check the coordinate system to make sure that it agrees with what I believe is the coordinate system I'm supposed to be working with. And now I'm just going to save my project. In that folder, it's saved as in an XML format. I'm going to start by using LAS File Analyst to review the LAS files to see if they are compliant with the LAS standard, with project requirements, and identify some other potentially meaningful information about the data. So remember, to do this, you right-click, and this can only be done in standalone LP360. We're going to right-click on the LAS layer and select LAS File Analyst. If all of the columns of information are not showing, you can toggle the Show Hide LAS File Header columns to make sure that all of this information is displayed, similar to what you see when you add LAS files to LP360 using the Add Files dialog. A couple of basic things to check right at this early stage is the coordinate system, for example, the version of LAS file format, which in this case is 1.4. You can also copy all of the information that's in the LAS File Analyst dialog using the Copy to Clipboard button over on the right-hand side, and then paste that into an Excel spreadsheet, for example, which might be useful if you want to do any calculations or additional sorting. Note also that as I'm going to have to make this window smaller so you can see, but as I select rows, I can also see which tile has been selected using this Enable Window Centering of Selected LAS Files option on the File Analyst toolbar. Next, let's scan the information and analyze the results for all of the LAS files. I'm going to select all of them and click on the Scan button to allow LP360 to go through and gather the necessary information from the individual files. Next, we'll run an analysis to compare the contents of the files to the LAS specification. So I'm going to select. I have to set my analysis options. Remember, I'm going to say I'm going to use all the LAS tests. Apply that, and now I have all the files selected, so I can go ahead and analyze them. Once the process is complete, you can see we have a red X here, which means there's something that didn't pass. We can simply hover over the X on a particular line to see the results for all of the different fields. As you've seen earlier, once you've identified any problems that there might be with the analyze function, you can repair. Again, you have to select your tab, specify what your information you're using to perform the repair, save that, and then performing a repair involves writing to the LAS file. So you need to make sure that your files are in read-write mode. So I will select all of them, and then over in the pane say open selected files for read-write. And now I can apply the repair. Okay, that repair took some time to run, but notice now that it's complete, I have a warning in the Analyze column, which again I can, if I hover, I can see that I do have a warning here, but the EPSG code error has been corrected. So now I can change the files back to read only. Oh, I have to select all of them first. Okay, and now we're ready to continue on to the next phase. The first part of this demo using LAS Final Analyst was a little bit of a review. The next thing we're going to do is generate some point density images, and this will be new. We've discussed the importance of point density and the importance of locating voids in the data as part of the very early initial QA/QC process. And there are some very convenient tools in LPRI 360 that help us do this. If you recall, point density images are created using the export LiDAR data command. So in order to be able to export the LiDAR data, we're going to need to actually load it. Remember, we loaded the footprints only. So again, I'm going to have to select all the files and right-click and say Load Selected Files. And now notice the CAN icons will begin to fill up, and I see the data actually appear on the screen. Okay, next let's open the Export LiDAR Data tool, the Export Wizard, and start figuring out how to set this up to create point density images. We're going to create a surface that's going to allow us to select a surface method. And in this case, we're going to use a surface method called point insertion. Okay, what are the points that we're going to use as source points? In this case, we don't want to count every single XYZ point that's in the LiDAR point cloud because some of those are secondary returns. So for point density, we're really only interested in how many original shots were there, how many LiDAR pulses, and did the pulses meet the point density requirements. So we're going to use first returns only. So we're only going to count each outgoing LiDAR pulse one time. So we're going to go to the return combinations and say first returns. Okay, that's an important requirement when we're creating point density images. We only want to count 1 point per transmitted pulse. Another important criteria for evaluating point density is we don't want to double count points in overlapping swaths in the overlap area. So we can eliminate this in one of two ways. If flags have been set in the data to identify overlapping points, we can simply use that flag, and that will basically filter based on that, and we won't count points that are marked as overlap. If overlap is not specified, we can also use the swath width or the scan angle, and rather than going all the way out to the edges of each swath, we can limit the scan angle so that we're really only in the center or the non-overlapping portion of the swath. And that's what we're going to do in this case. We're going to filter based on scan angles, and we can key in the scan angles that we want to use. So we're going to use negative 13.5 degrees, and this would not be the same for every single project. These scan angles are specific to the way this LiDAR data was collected based on the swath width and plus 13.5. So from negative 13.5 degrees to positive 13.5 degrees. So we're going to count basically only the points that are close to nadir and in the non-overlapping area. Now that I've got my source points selected, I can go ahead and set up the point density images. The first thing I'm going to do is select density as the surface attribute to export. This gives me the density tab that we're going to look at in just a minute. The next thing I need to do is set the cell size or the cell edge length. Remember that this is supposed to be 2 times the desired nominal point spacing. And someone has to tell you what the desired nominal point spacing is for the project. That would be part of the contract or the project specifications. So for this example, we will use the requirement for USGS level 2 data. It's supposed to have a 70 centimeter nominal post spacing. 2 times that would be 1.4 meters. We are working in feet, so we'll convert 1.4 meters to 4.6 feet, and that will be our cell edge length. Now let's click on the Density tab. We want to produce a graphic output, a raster image, and we're going to color code the cells by point density. So remember that point density is the inverse of the cell area. So in this case, if the cell size is equal to 4.6 feet, then point density is equal to 1 divided by 4.6 times 4.6, which would be the cell area, and that would be 0.047. Okay, we're going to then create some intervals of point density that will color code the cells. So if it's a void cell, it will be black. If it has a density from 0 to 0.0157, it will be red, and so on. So cells that are green have a point density of at least our target, which is 0.047. You can, if you wish, customize the colors, but I like to leave black as void. Red is a alarmingly low point density. Orange and yellow marginal, and green is acceptable. So next we'll go ahead and select the area of interest. I'm going to pick a small area just in the interest of time. I'll use the draw window tool. Just pick a couple of tiles. Next, I'm simply going to specify the resulting export file. It's going to go into my project folder. I'm going to give it the name NPS for nominal point spacing. The raster will be generated as a TIFF file, and I'll have it insert the output to the map. So at this point, I just click Finish and wait for that to process. Right, that took a few minutes to process, and we see the result. I'm going to turn off the background LiDAR data to help us see the result a little bit more clearly. We can see that we've achieved the target point density over much of the area, but there are clearly some voids. I'm going to turn on some background imagery to help interpret those voids. And I can click the density image on and off and see that clearly there are some voids over the river water body, which is to be expected. But there are some other voids that don't appear to be over water bodies. For example, in this area here. Okay, so remember that we chose a swath width. We chose to not look at points beyond a certain scan angle. So that looks a bit like we may have just cut off a little too much data in the overlapping area. So we could go back and rerun the density image and change the scan angle requirement a bit and see if that indeed would fix that kind of a problem. And then notice that there also are some kind of void areas in the downtown where there are some tall buildings, and that's most likely due to some shadowing effect. In other words, the LiDAR didn't reach the ground in those areas because it was blocked by buildings. So at this point, as the person responsible for this preliminary QA/QC, you would need to decide if it would be appropriate to go back and either change some of the settings to create your point density images. In the case of the scan angle, if it would be appropriate to adjust that, or whether there are some other acceptable physical reasons for there being some voids in the data. Okay, I went back and reran the point density images using a little bit larger scan angle. So I went from -20 degrees to +20 degrees, so including a little bit more of the edge of the swath. And here is my result. And you can see that indeed took care of most of those little slivers where we suspected that we might be cutting off too many of the overlap points. If we look down in that area where there were a lot of buildings, we see that by including a little bit more of the data on the edge, we also filled in a bit more of those void areas in the downtown. And let's look at there's one other area of interest, this area over here. Okay, it clearly doesn't, even from the shape, does not look like a water body. So I'll reference the image again and see that it's actually a building with a very dark black roof. So this is a case where most likely that black roof was so absorbent and acted similar to water, where we just did not get any LiDAR returns off of that material, and it creates a void in the data, again, similar to water. In a case like this, where we have a localized void that can be tied to a physical explanation, reflying the data again is not likely to produce a different result. So this would be allowable, however it would be documented in the QA/QC report. At this point I'm going to switch over to LP360 in ArcGIS. So I'm going to save my project, and those TIFF images obviously have also been saved in my project folder, so I will be able to bring those directly into ArcGIS. So here I've opened my project data in ArcGIS. I brought in the LAS layer, and I'm using the orthophoto image as the backdrop in this case. And I've loaded in the second of the density images that I created with the -20 to +20 degree scan angle. So I'm going to turn that on in the display, and the first thing you'll notice is that the colors are different. So Esri, in their infinite wisdom, creates some default symbology for images when you bring them into ArcGIS. So let's take a look at the image symbology. And notice that we've got a stretch type applied, including a gamma stretch. So without going into what these are or why they do this by default, let's just turn off the gamma stretch, because the way LP360 created these images using the red, green, and blue bands, they were written to a file such that they would create the colors that we set up in the legend. So let's apply that, and lo and behold, now we see that it looks more like we expect, where the colors that are in the density image match those that we set up in the legend when we created it. So now that we know that some voids can be physically explained and are in fact unavoidable, how do we decide if the dataset is acceptable or not? The USGS has established some guidelines in their LiDAR-based specifications, and while these don't necessarily apply to every LiDAR project, they are by default one of the most comprehensive treatments and explanation of all of these QA/QC requirements and procedures. So we're going to take a look at what they say about data voids. There is a section that provides a definition of data voids and also explains the circumstances in which they're acceptable. For example, when caused by water bodies, when caused by areas of low infrared reflectivity, or where filled in by another swath. It also outlines the procedures that we've already used for creating point density images to evaluate this. At the end of the day, the requirement is, excluding the acceptable data voids as previously identified, the remaining cells in the density grid, at least 90%, must contain at least one LiDAR point. In other words, 90% of the remaining cells need to have achieved the required point density. How this 90% is determined quantitatively is a GIS process that goes a little bit beyond the scope of what we want to focus on in this course. For this section, really the important takeaways are: what are data voids, when do they naturally occur, and how can you detect them? If you'd like to see a little bit more in depth how to perform this quantitative analysis of the 90% of cells, take a look at the LP360 training materials for this tutorial section 200, where they explain how to use the ArcGIS model builder to perform this analysis.